예, 안녕하십니까. 중앙대학교 문장입니다. Yeah, welcome back. I'm a assistant professor at 중앙 University. Today we are going to discuss about the structural vibration. So that actually this structural vibration is slightly out of scope our the lecture. However, it is because that solid mechanics only consider the static cases. However, the all solid structure can move and freely translated, so that I think that dynamics also strongly relate to the structural analysis, so that I'm going to cover the structural vibration in this lecture. So maybe the 2 weeks we are going to spend the 2 weeks more, yeah, slightly, so that please follow the more detail. So that these contents are included in the chapter 16, but I cannot give you the very complex problem to you guys. However, it will be very helpful to when you understand this concept. Yeah, you guys can easily answer the problem when you are in interview for your job market. So I think that Professor O already teach you about what is the vibration, and however today I'm going to very briefly introduce the basics equation of the structural dynamics from the single degree of freedom to the multi degree of freedom system. Yeah, vibration is very important. It is because that it can result some malfunction or breakdown of the some machine due to the, and also in this result in the unbalances or misaligned, so that so it makes a lot of trouble when you are when you meet some when you handle some mechanical component. So that so however, the vibration we cannot catch the by our eyes. So the simulation is play a very important role to understanding the structural dynamics behavior. So I think that you guys already learned about the vibration or dynamics in analytical formulation. Yeah. However, using the simulation, FEM is one of the strong candidate is a simulation method for the understanding the dynamics method. It is because that I think that in the Professor O's lecture, he also introduced the some degree of freedom of the system. So at that time, some masses are considered a point masses, so that it's a very similar some specific node, that it looks like point masses, so that it's equivalent to the node. So that means that, yeah, I think that there are some matrix equation is the same form our FEM matrices equation. I think for more details, stiffness equation. So I think that you guys already know that about the dynamics equation in the FEM formulation. But yeah, let's before we start, we should know that the three different types of the dynamics problem. First is modal analysis. Second is frequency response analysis. Yeah, third is transient response analysis. Yeah, among them, the transient analysis method, which I already show you the some beam transient behavior using the COMSOL simulation. So that this transient response is some dynamic response due to the some external arbitrary external forces. So that when you apply the any forces, arbitrary forces in here, the beam will be bended and then fluctuated depending on the forces. However, yeah, this transient response analysis take more spend a lot of time to obtain the solution, and then need high computational power. Actually, in our cases, 1D cases, you guys can easily obtain the. However, just think about, we have a very complex 3D structure. So at that time, we have a lot of degree of freedom. Yeah, it takes a lot of time. Just think about in the static analysis, we only solve the only one single cases. However, time transient analysis means that we should solve this equation every time step. T equal t0 plus t equal n. So that you should solve this equation every too much time, so that those kind of way we need actually time transient analysis need a lot of computational time. So to reduce this computational cost, two methods are introduced. The first is frequency response analysis, the other is modal analysis. Frequency response analysis means that we are going to apply some harmonic oscillation external forces in this system, and then we are going to fix some external magnitude of force, and then we are going to changing this W angle of velocity or some frequency of these forces. Depending on this frequency, this solid structure will respond. Due to the very high frequency, solid structure doesn't. There are no big movement. However, proper frequency generated large movement. What is this? This is a resonance. 공명. In Korea. So that so those kind of way we can test it depending on the frequency of the external forces. We can predict the deformation of the solid structure with actually this is not the dynamics analysis, but the time dependent dynamics analysis. However, frequency is strongly related to the time, so that this is also different types of the time dependent analysis. Am I right? So that last one, actually first one is modal analysis. In this system, we do not apply any external forces. This part, force is always equal to 0. So that we only check the system itself, without considering any external boundary, external forces, force boundary condition. But we are going to handle the only boundary, fixed boundary condition or displacement boundary condition, depending on the cases. However, just to think about modal analysis is a pure system behavior or responses. So this modal analysis is strongly related to the frequency response analysis. However, in here we are only check the specific responses, frequency dependent responses only. So it's a slightly different. But however, in here we don't consider any external boundary condition, external forces. So that means that we don't need too much computational cost. So and then due to the existence of the external forces, these external forces will change it or varies as function of the time. However, in here all forces are equal to 0. That means that it looks like a static cases. So that we don't need to spend a lot of computational cost in the modal analysis. That means that you guys can easily obtain some solution using modal analysis. So that in the before you guys started the time transient responses analysis, this modal analysis and then frequency response analysis must be done before you do this third transient response analysis. So this is a review of the basic equation of the dynamics. So this first is a single degree of freedom system. Some masses has attached with spring and damper on the wall, and then we are going to apply some forces in the right hand side. In here M is masses, K is stiffness, and C is damping, and F is forces. So that in here this is a free body diagram. You guys can easily draw the masses. So that, and then in the right hand direction that we have some external forces. The left hand side, due to the spring and damper, we have those amount of the some forces Ku. Yeah, this spring is proportional to the displacement, and then this damper is also proportional to the velocity of these masses. So based on this equation, you guys can easily make some dynamics equation. First, yeah, our mass, F equal ma, and a is can be represented by to the second derivative of displacement, but for more convenient, we are going to use those notations. Yeah, this dot means that first time derivative, so is equal to the first f t is equal to, and then but this also but negative sign equal to the c equal to u. So this is a force equilibrium equation, but static equation we can negligible acceleration and velocity, so that f equal ku is our main governing equations in our system. But in here so this is a main governing equation in the dynamics analysis of the single body system. So this equation, you guys, it's a very simple ordinary difference equation. So I think that you guys can easily obtain the solution with as a function of the time. So maybe we guys easily expected blah 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 plus exponential term with some depending on the some forces. You guys homogeneous solution and particular solution. So UH and UP, that was our engineering mathematics in your freshman years. So that anyway, due to the complexity, we are going to neglect the some damping coefficient, so that there are no damping in this system. And then first in the let's consider pre-vibration. Pre-vibration means that we don't apply any forces in this system. Finally we obtained those kind of very simple pre-vibration equations. So to solve this equation, we assume that our solution, depending on your system, actually you guys can easily assume that exponential equation, but in here the sign is enough to match to this result. After the second time derivative, you guys can obtain the omega 2 and sine, and first cosine, second is sine again, and then we need some minus sign in here. So after then you guys can put this in part in here, and then second is u is we assume that this solution, they followed this solution in here. So okay, so we have the same things in here, u, and then sine omega t, and then a bracket with the remaining things omega m k equal to 0. So we obtained those kind of equations in here. So actually in here we have some we met some problem. Just think about sine omega t. We assume that as sine, these values are varies as function of the time, so that it cannot match the equal to 0. Sometime it can be 0, but almost cases does not equal to is not equal to 0. So that means that it is hard to match to this equation due to this part become 0. So that, and also u is an arbitrary value, so that we just assume that this is an arbitrary value, so it looks like a magnitude of the displacement. So that only remaining things, this part must be equal to 0. So that, yeah, due to the non-trivial solution, yeah, so yeah, the non-trivial solution means that, yeah, this part also can be equal to 0. However, in the previous slide we assumed that the solution followed this result. However, when the u, capital U, equal to 0, that means the total solution becomes equal to 0. So yeah, we don't need to those kind of result. Yeah, we say that this is a vibration motion, dynamics motion. So that means that we should obtain the displacement as a function of the time. However, in here there are no movement in here, so that means that we don't need to those kind of this kind of non-trivial solution. So that, yeah, we must have the match those kind of relationship, and then, yeah, this omega in the frequency in here must be equal to, looks like this. Yeah, this is a natural frequencies. Yeah, we call it the natural frequencies in the single degree of freedom system. So I think that, yeah, so when you apply some forces, yeah, same these natural frequencies, so that, yeah, in the previous slide maybe, yeah, we had in here, in the pre vibration we assume the external force is equal to 0. However, yeah, when you say that, yeah, we are going to apply the same frequency, yeah, it looks like a harmonic responses in the second cases. So that at that time, so that we can meet the some resonance behavior. So that anyway, yeah, in the pre-vibration mode, yeah, so that the solutions are looks like this. So that in the, this is a frequencies of this free body diagram. The u is a non-trivial some arbitrary values depending on the how their initial condition. So solution, you guys can easily obtain these solutions. Yeah, so yeah, although I neglected damping coefficient, however, when you guys consider the damping coefficient, and then, yeah, I skipped the more details. Just review your engineering mathematics, and if you assume that, yeah, this is critical damping coefficient, and then, yeah, if our damping coefficient is lower than critical damping, so that solution or relationship, they have those kind of relationship. And then finally, solution, yeah, damped by vibration. Actually, we don't have applied any damping coefficient in these equations. So due to the existence of damping coefficient, in the previous slide, yeah, natural frequencies, yeah, total frequencies become the damped frequencies. So that, yeah, this gamma is delta is represented by the ratio of their initial their own damping coefficient with respect over the critical damping coefficient. So that, yeah, if you however, in the structural damping structural analysis, if the damping coefficient has below the 0.1.5, yeah, we assume that, yeah, damped vibration, damped frequencies are similar to their natural frequencies. So that, yeah, this is yeah, although I do not explain more detail, so and then we can ignore the damping system. So that at that time, so we assume that very simple, yeah, natural frequency system. So due to the damping coefficient, actually their responses looks like this. Yeah, so that the magnitude of the damping behavior are decreased. So that this is a role of the damping coefficient. So that it is because that, yeah, this damper shows generated forces in the opposite direction in their by the velocity. So, yeah, this damper will decrease the magnitude of the vibrations. So anyway, yeah, let's go to the next. Yeah, let's consider the multi-degree of freedom system. Yeah, although we are going to consider the more degree of freedom system. However, the equations are has the same form in here. So yeah, m is a mass, u dot double dot is a acceleration, and then c is a damping, and then k is a stiffness. However, yeah, u is has some vector form depending on your system. If we have a element truss system or 2D system, or depending on your two-dimensional cases, we should add those kind of variable in here, v, so that depending on your system, u has some, you can say that vector form. So that means that k is stiffness matrices, and then similarly, damping, in here they can change in the matrix form, and the mass also has a matrix forms. So these equations it's slightly different compared to the single degree of freedom system. So you guys can easily know that this part, f equal ku. However, in here, we should define what? Masses matrices and damping matrices first. But we usually neglected damping matrices, but we cannot neglect mass matrices. So in here we are going to learn about how to define the mass matrices for the FEM simulation. Here, mass. First we should consider the mass matrices first. To define the mass matrix, we have two different types of the mass matrices. First is a lumped mass matrices. Second is a consistent mass matrices. First, lumped mass matrices is more empirical and easier to determine, or you guys can easily understand lumped mass matrices. However, second one, consistent mass matrices is some mass matrices derived from using our shape functions or some analytical formulation. So it's more accurate than lumped mass matrices. However, in this time, you guys can easily derive the consistent mass matrices either. But let's handle the lumped mass matrices first. Let's begin to the truss element first. We have two nodes and then 2 degree of freedom. This displacement element, and then this element has a specific length and cross-section area. And then to know that mass, we should know that density of this truss element first. How can we obtain the total masses? You guys know that the density, you should know that total volume. So that what is the volume? In here, volume is a multiplication cross-section area, the lengths. This is a total masses of this truss element. But we can only handle some material property, other displacement or other forces only at specific nodal point. Our FEM, inside or middle of the element, we are going to interpolate it. So all values must be defined at nodal pointed. So that we have two nodal points. That means that total masses are equally distributed both node point. So that means that total in the half values are masses in the first nodal point, and then the other half is masses in the second nodal point. This is lumped mass matrices. What is the assumption? If this masses, okay. So sometimes this assumption is very correct or easy to define. However, sometimes it's slightly different. Just think about if we have two different cross-section area, some truss, but we don't dealing with those kind of structure. But I gave you those kind of structure to you as homework in the first or second homework, so that at that time we cannot say that same lumped mass matrices. So that at that cases we cannot use lumped mass matrices very easily. So that actually this lumped mass matrices has some limitation. So that this masses can be consist of those kind of can be transformed to the matrix form, and here so we are going to apply some accelerations separately. There are no coupled term in the first and or second equation. So this is how can we determine the lumped mass matrices. And then second is let's constant mass matrices. Constant matrices has those kind of analytical formulation. So actually you guys can easily think about what is the total masses. Density can be integrated whole volume area. So this is can be total volume. So however in here we have some problem. Why? What is this one? N is a shape function. So in the FEM method, we already learned about several different types of the shape function depending on your system. But in here you guys know that the exact shape function, after multiplication of the transposed shape function and the shape function, they returned some matrices. So that after then you should, after the integration this shape function, so that you guys can obtain the constant mass matrices. This shape function is you guys can say that as function of the x or y or g. So generally in the 1D cases this function can be as function of the x only. But in our stiffness matrices equation, this shape function generally derived by some axis, so that becomes some constant value, not a function of the axis. However, in here, so they have a function of the axis. That means that we should take some numerical integration in here. But this is next work. But anyway, so how can we? Why we need those kind of shape function first? Similarly, deriving the distributed forces. So let's consider the kinetic energy first. What is the kinetic energy first? Kinetic energy is 1/2 is mv square. So but v is a time derivative of the displacement. So that means the v square. We can say that some multiplication. Velocity. It is because the u is a vector, not scalar anymore. So that this result can return the scalar. So this in here v kinetic energy is a scalar, and the masses is a scalar specific point, and then vector. So v must be equal to scalar. So that however in the u is a vector, that means the v square we can represent it looks like this. In here, so we can say that the kinetic energy is multiplications of the u transpose and mass matrices, and u velocity vector. So then in here, so that mass is a total integration of the density with respect to the volume. So that we can say that in here, so and then we can deduct divided looks like this. And then in here, what is the u? U is a variable. However, we can discretize this looks like this, and maybe in here the u is we use some bolded u, represented vector form. However, this u can be discretized looks like this. This u are slightly different. U is a function of the x. So shape function is a function of the x. However, ui is some scalar values which obtained from after the calculation. So that this is not the function of the x anymore. So that those kind of 잠깐 한글로 설명하면요. 저희가 계속 U라고 하는데요. 저희가 아날리틱하게 고체역학이나 뭐 동역학 시간에 뭐 변이를 갖다가 X나 T에 대해서 얻을 수 있으셨죠. 근데 그게 아니라 저희가 유한요소 한다는 소리는 뭐죠? 디스크리타이즈해서 딱 포인트에서만 값을 얻는다라는 거죠. 그 사이는 서로 인터폴레이션 하겠다라고 하는 게 주된 핵심 내용인데요. 즉 이런 U를 갖다가 쉐입 펑션 곱하기 노달 포인트에서의 변이 값으로 이렇게 치환해 주는 것을 저희가 뭐 한다? 디스크리타이즈 한다 라고 표현을 하죠. 그래서 잘게 쪼갠다 라는 뜻으로 하기 때문에 뭐 이렇게 표현을 하고 있습니다. 어쨌거나 let's begin to the lecture again so that U velocity can be discretized looks like this, and then after the applying the transpose, so in here here this is a velocity of the system, and then the remaining part is equivalent to the masses, so that those kind of way we define the consistent mass matrices looks like this. So in the truss element, let's consider the truss element. In truss element, how can we define? Maybe shape functions was look like this, and then for more convenient, we are going to use those kind of shape function. Chrono delta is range has those kind of ranges, so that after the taking here, so that we after the multiplication, so maybe they become those kind of matrices. So and then total volume can be changing the cross section area total. Slightly wrong. So anyway, I don't think so. This is a total psi, so that this is a total volume, so that after you guys need the integration from to the depending on the from to 0 to 1, so that rho a, and then so sorry, I think that this is correct. So it is because that they mapped this element from to 0 to 1 from where 0 to L, so that we need this is L is a Jacobian in here. So this is correct. So that finally we obtained those kind of mass matrices, so that exactly 6 over rho a L 2 1 1 2 is this is a lumped mass matrices. Compared to consistent matrices, compared to the lumped mass matrices, in the on the off diagonal term, they have some slightly value. So I'm not sure that why these two masses are coupled to each other. So however, in the depending on the system, sorry, actually 1/3 came from the contributed from the first nodal point, and then 1/6 can be contributed from the second point masses. So that depending on your system, this lumped constant mass matrices can be changed, so that in here we assume that cross-section areas are always equal to same with respect to the element. However, if they have a different cross-section area, so that at that time, although we need more cost to integrate these parts, so that however you guys can obtain the more accurate mass matrices compared to the lumped mass matrices. This is how can we define the element, so that although let's consider the beam element. I don't think I teach you guys about about the shape function of the beam element. I just derived from the Carbonic equation, but I don't think I defined the shape functions of the beam element. But in the our main textbook, they have some shape functions. It is in the beam element they have 4 elements, so that they have 4 elements in the shape vector, so that after the multiplication, you guys obtained those kind of constant mass matrices for the beam element.